Next up, we've got Konstantin Klinger with identifying malware using Bloom filters and DGArchive in a sandbox environment.
Hello, everyone. First of all, thank you, GRIMMCon, for having me again. I really enjoyed speaking in April, and I'm happy to be back. My name is Konstantin Klinger, and I'm currently living in Bern, Switzerland. I work as a security research engineer within Proofpoint's threat research team. I focus on malware analysis, actor tracking, and detection signatures. And I would like to talk today about how to identify malware using Bloom filters and DGArchive in a sandbox environment. So this talk is really technical. It's all about the usage of so-called Bloom filters within sandbox environments. The goal of this project has been to develop a proof of concept to use Bloom filters for massive key value lookups in sandboxes. The domain generation algorithms are only used as an example for this method. I would like to check all DNS requests from a sandbox run against the Fraunhofer DGArchive to first detect that the DGA has been used, so for detection purpose, and second, to label the malware family for classification purpose. Based on this example, I'd like to present the advantages of such key value lookups in sandbox environments to raise the demand of its usage. Let's look at the agenda for today quickly. I will explain the motivation of this project by showing you the status quo, how DGAs are getting detected in sandbox environments at the moment. Before I'm able to show you how the detection signature creation works and how its outcome is, I will have to introduce you into some basic background knowledge that is necessary to understand. So you will learn the basics about domain generation algorithms. You will learn about the Fraunhofer DGArchive. You will learn about sandbox environments, in specific the Cape sandbox, and you will learn about Bloom filters. Finally, I will show you the process of signature creation and talk about the results, the limitations, and give you an outlook what other questions are possible to answer with Bloom filters in sandbox environments. Let's start with the motivation. DGA domains are currently only detected in sandbox environments by signatures that rely on hard-coded values. In the code snippet on the slide, you can see that the signature depends on the length of a domain and that it also depends on hard-coded top-level domains. Here. But there are plenty of other DGA domains that do not fit into this approach and will let the signature not fire on it. So that's a problem. The signature is not fed with any threat intelligence or IOCs, which means that known DGA domains are not detected and checked against the DNS requests of a sandbox run at the moment. So this is a common problem in sandboxes. Sandboxes have to process tasks really quickly, and therefore it's almost impossible to check the forensics of a sandbox run against your threat intelligence knowledge while execution. That's why the idea of this talk and this project is to develop a proof of concept for better IOC matching in sandbox environments using DGA algorithms as an example. Before I can go into detail about the signature, I will have to introduce you into some background knowledge. So we will answer the question, what are domain generation algorithms at first? A domain generation algorithm, short-term DGA, is a program that calculates a list of domains dynamically while being executed. Those domains are used for command and control communication by the malware. Many DGA algorithms use time as an input parameter. So depending on the current date, the calculated DGA domain is different every day. Attackers are using DGAs to avoid hard-coded values for C2 domains and to be able to quickly switch C2 domains and the IP addresses beyond the domains. So they can quickly switch IPs and domains to hide themselves in the network traffic. This makes it harder for defenders to detect, block, and take down malicious infrastructure. They have to decode the DGA algorithm to get the full list of domains in order to block all of them, because in a dynamic run of the malware, only the current active C2 domain gets requested that has been calculated by the DGA, and only this domain will be seen in the network traffic. Of course, attackers have to register those domains before using it as a C2 server, and in this way, they also have control in a sort of active switch in their hands. So I will demonstrate this concept in the picture. You can see an attacker that sends a malware to the victim's machine, and it runs on the victim's machine. The DGA calculates a domain and two fallback domains, which are getting resolved on the DNS server. The malware can't get a DNS response for the first two domains, so it has to take the third one for which it gets a valid IPv4 address. Then, finally, the malware is able to start C2 communication to the C2 server. In this case, we have three DGA domains, and for example, on the next day, those three domains look totally different. So it's really hard to keep up to date with those domains without help. Another example I would like to show you, because it's from recent interest, is the recent supply chain attack on SolarWinds. The malware that is called Sunburst from FireEye uses a DGA to calculate a specific subdomain for every unique victim machine. This is a good example where DGAs are used and not time is used as a seed for DGA. In this case, the GUID of the victim's machine and the hostname of the victim's machine is used. So you can see on the picture that the subdomain is decoded based up on those values. And in this case, DGA is not only used as C2 communication, but it's also used to exfiltrate data because, for example, the hostname of the infected machine is sent to the attacker, and then the attacker can choose based on the hostname which victim is interesting and which victim is not interesting. But also defenders are now, with the publication of this supply chain attack, able to decode the encoded hostname and then look what victims are there of this attack, and then they can warn them in advance. So DGAs are really seen often, is the message you should keep. Next background topic. So what is the DGA archive? The Fraunhofer DGA archive is the largest collection of known DGAs and their domains. So it stores the DGA algorithm and then it calculates all of its domains. So there are around 100 different malware families with up to 100 unique DGA domains. As a security researcher, it's possible to get free API access, and the people that are developing this system are really happy for contributions. For example, if you detect a new DGA and a malware, please send them a seed so they can add it to the collection, and then you also help the community. There are around 500,000 active DGA domains every day. And a bit confusing is the definition of 1 day, because 1 day is actually 3 days if you take the active domains from today, yesterday, and tomorrow to cover all possible time zones. And this is called 1 day, and there are around 500 active DGA domains every day. So now that we know about the DGAs in general and the Fraunhofer DGA archive, which collects DGAs, we can quickly recap what is a sandbox, in specific, what is the CAPE sandbox. There exist various different open source sandboxes. CAPE is only one of them. And there is a free community edition available online where you can submit samples for free. Of course, there are other services. I've chosen the CAPE sandbox for this example because it was pretty easy to implement the stuff I wanted to have. The concept of sandboxing is always the same. You submit a sample, it gets executed in the sandbox dynamically, and then you get a report. Sandboxes are really helpful for malware analyzers to detect malware on the one side and to extract payload and configuration from malware on the other side. It's possible for defenders to automate many tasks that would take long when they would reverse the sample manually. In CAPE, because it's derived from Cuckoo, it's possible to write behavior signatures in Python on the dynamic execution of the sandbox run. So how the malware depends in the dynamic run, you can match on that behavior with Python signatures. For example, for our use case, I can do things with the DNS requests of every sandbox run, which you will see later when I explain how the signature works. What is a Bloom filter? A Bloom filter is a probabilistic data structure that is based on a concatenation of unicache functions. It has been invented by Burton Bloom in 1970, and that's also where the name comes from. In the security research field, Bloom filters are often used to answer queries if a given object set may be a member of the Bloom filter, or if it is not a member of the Bloom filter. This answer is provided in constant time and with a small amount of space used, but with the limitation of a pre-known false positive likelihood. I have to explain this a bit better. So a Bloom filter guarantees you the answer no for a membership check, but it's not so sure about the item if it exists in a set. It also tells you it maybe exists in the set. There is a very high chance that it exists, but it's not guaranteed. This false positive likelihood, which is also called error rate, can be configured for every Bloom filter, as well as the size of a Bloom filter or the number of entries. Additionally, a Bloom filter is a good way to store sensitive information, e.g. personal data, login credentials, or customer data, as it is not possible to reproduce the original data of which the Bloom filter has been created. So that's an advantage that comes with this data structure. We now know about DGAs, we know about the Fraunhofer DGA archive, we know about sandboxes, and we know about Bloom filters. So we are able to look into the detection signature creation. And at first, we have to choose a Bloom filter library. If we want to create a signature for a sandbox run in Python, we need to choose a library or implement our own for Bloom filters. So I've decided to compare different existing libraries against each other and against the usage of regex engines. For this benchmarking, I've used a Bloom filter with a size of 1 million and an error rate of 0.01%. And I've inserted all active DGA domains from a specific day, which are around 500,000, as I've said earlier. We compare this Bloom filter against a normal regex with the domains in raw with a lot of logical ORs, and an optimized version using a Perl script that can calculate optimized regex with a given list as an input. We use the timeit library to measure execution time on average over 10,000 iterations. If you look at the code snippet, you will see that below. And we measure the time, how long it takes to check 100 known DGA domains against the regex and against the Bloom filter, and then compare each other. And of course, we measure the time for different Bloom filter libraries. That's how the results are looking. The OR regex was pretty bad with an execution time with more than 1000 milliseconds. So the time is in milliseconds on an average over 10,000 iterations. The Perl optimized regex was really good. It's marked in yellow, and with an execution time on average of 1.02, it's pretty quick. The regex2 library, I could not load it because I got a strange compile error because the regex, the import of my regex was too big, so it's simply not possible to create a regex with this engine. But I had not the time to look into that error more into detail, so maybe I can find a way around it. But I think we have a good benchmark with the normal regex, which is marked in yellow. Of course, native Python solutions are slower than solutions that are implemented in C and then can be used in Python. So that's the reason why you will see the two green libraries that are really good, because they are implemented in C. But both have some limitations. So InBloom has a bug so that you can't load the Bloom filter from a file, and Bloom filter mmap3 had also some issues. So there were some memory leaks, and I simply could not find out what's wrong there. So in the future, I would like to use a library that's marked in green because they are really, really quick. For this project, I've chosen the Flow library, which is marked in blue, because it was the best native Python solution that I could find. And it's also maintained. And for the proof of concept, it's not necessary to go with the quickest solution at first. So when it comes that the signature will improve things, we can choose another Python library and then use one of the green ones. So that's the goal for the future. One thing I have to add is that, of course, it's also possible that you can play around with size and with the error rate. And if you play around with those parameters, you can also get different results here. So if you increase the size of indicators you want to check, and if you don't use 500,000 domains, but more, the Bloom filter will always be better than the regex, but also the native Python solutions of the Bloom filter are getting better with more indicators. So the regex gets more bad and bad and bad, but the Bloom filter is getting better and better and better. So it scales with many IOCs. Now we have everything we need for the signature. We've chosen a Bloom filter library, and we can now proceed looking into the signature workflow. A malware gets executed in the sandbox, and some of them are doing DNS requests. If they run successfully, some of them are not doing any DNS requests, but we will check all DNS requests from every sandbox run against the Bloom filter in this step. And the Bloom filter contains the active DGA domains from today, tomorrow, and yesterday. This first lookup is really quick because it's in the nature of the Bloom filter, and we will only proceed to the next step if we have hits. One thing to notice that we don't know if we only know at this point that the domain may be a DGA domain, but we are not sure if it is because it's also in the nature of the Bloom filter that we could have a false positive. The second lookup here is we will check the hits against the dictionary that has been loaded into memory when reloading the sandbox once a day or once an hour with new signatures. So in this way, we can connect the DGA domain to its malware family, and we can confirm that the hit from the first lookup is a true positive and not a false positive. This second lookup is slower, but it is only done for hits of the first check, and therefore you don't have it really often, and not for every DNS request of the sandbox run. So of course we could improve things if we would be able to do the second lookup against an external server or against a microservice that runs on the sandbox controller. So those are all good ideas which we have some room for improvement in the future. In the end, the signature returns true or false. So if both checks are successful, then we return true, and if not, we return false. I've posted links on the slide where you can see the signature because I was able to contribute that into the CAPE v2 code, which is also available in the free community version. Let's look at what the results of the signature look like. So after a few months of testing, we were able to identify a lot of malware and add additional classification labeling to the sandbox forensics. So for example, sometimes we were able to detect malicious behavior, but we were not able to detect the malware family or the DGA family. And with this new signature, we were able to do this. And then we could add that classification to the sandbox run, which improves things when it comes to threat hunting and threat intelligence. At first, the signature needed some tuning. So the first month was really hard. We had to remove the Alexa top 1 million domains because a few DGA domains that were active on a specific day were also in the Alexa top 1 million list. So they were legit domains. And of course, we don't want to have hits on that. Also, we found out that we have to remove really small domains because it's simply not good enough with small domains. We also had a few false positives. Further, we removed a few DGA families, mostly the dictionary-based ones that do not rely on time as an input seed, for example, Superbox, because they also match on legit domains. And on the slide, you can see the Railroad DGA family, which is a simple regex of A to C up to 6 digits and 6 characters. And that's something we had to remove because we had false positives. But after this tuning period, we have not observed any further false positive. We have observed over 20 DGA families, and in over 90% of the hits, we had only the new signature firing and not the old one, because as I've introduced in the beginning, the old signature relies on hard-coded values and top-level domains. And now we can check against a list of 500,000 active DGA domains, which of course improves the situation. Another thing to add is that we have great performance metrics. So even though the second lookup against the dictionary is really slow and we can't use a microservice at the moment, it's really quick. And you can match 500 IOCs in a sandbox environment at scale. So we are now able to match huge numbers of IOCs in sandbox environments in really quick time. And it works, even though we use the slower Bloom filter library, and we could improve things in the Cape sandbox if we would use a microservice for the second lookup. That's also the limitations we currently have. So of course, the update mechanism is a bit complicated. You can run the Bloom filter creation script as a cron job, or you can run it manually on your device and manually push the Bloom filter to the sandbox controller once a day, or how often you decide. But if you don't do it every day, of course, the Bloom filter is outdated after a few days. So I have increased the community repository size of about 7 megabytes because the dictionary is 4 megabytes and the Bloom filter is around about 3 megabytes. We have chosen the slower Bloom filter library, which could be better. We have chosen the slow second lookup, which could be better. So all in all, the results were really good already, but there is room for improvement. Let's talk about what we can do besides working on our limitations. So the initial idea was that we have a proof of concept for better IOC matching in sandbox environments, and we use the DGA as an example. Of course, we could expand that to other examples. We could match, for example, against the Alexa top 1 million domain list and create a function in the sandbox, which name is Alexa top 1 million. And then we could quickly check every domain if it's in the top 1 million list. Second, for example, we could export IOCs from our MISP instance and then check all sandbox forensics against that list of IOCs, because we have proven that with Bloom filters, we can match really quickly in sandbox environments, huge numbers of IOCs, and it scales. So this works. But you can also think the other way around. You could create a threat intelligence feed out of sandbox forensics. You could create Bloom filters and so-called CNET files from sandbox runs that collect all domains that have been observed in sandbox runs, and it's completely anonymized. We would not leak any customer data in it, because if you check against this Bloom filter, you only get the answer that something may be in it or something is not in it, but you can't reproduce the initial input that the Bloom filter has been created with. So that's something for the future. And I would like to thank you for your attention. I'm really happy to be back and to speak again after April. I wish you a better year than this year and hope to see you soon. I'm looking forward to your questions. Thanks.